Good afternoon, ladies and gentlemen. Thank you for joining us for the Rotating Machine Sections webinar today, where we talk about the refurbishment of SABS's world-class NEFTA high-power testing laboratory. Our host for today is Jabulani Bembe. He is the chairman of the Rotating Machine Section. Jabulani Bembe completed the B.Eng and M.Eng in electrical engineering from the University of Johannesburg. He also completed the B.Tech degree from Vaal Triangle Technikon. He holds the government certificate of competency in electrical and mechanical engineering. He has more than 20 years experience working in electrical machinery repair and research industry. He currently works for the South African Power Utility Eskom as a researcher specializing in asset condition monitoring. He is a member of the Institute for Engineering Council of South Africa and the South African Institute of Electrical Engineers and Institute for Mechanical and Electrical Engineering Council of South Africa, IMEXA. I hand you over to Jabulani.
Good afternoon, colleagues, friends, and those who are joining us today. We're looking forward to a jam-packed sharing of the things that the Institute is doing, especially the rotating machinery. But what I would like to do is I would just like to quickly introduce to you Rob, my colleague, who's going to be giving you a very interesting discussion regarding NEFTA, I mean. So let's look at Rob's bio. Rob graduated in electrical engineering from the University of Witwatersrand in 1993, where he developed a passion for electrical machines that remains with him until today. This passion resulted in his first engineering position at ABB AC Machines in R Road, South Africa. After almost 10 years at ABB, Rob moved to a small specialist condition monitoring company, Westwood Electric, but subsequently rejoined ABB a year later as a strategic development engineering manager. To feed his passion for rotating machines, failure analysis, diagnostics, design, maintenance management, and above all, problem solving, Rob joined LH Martinez in 2006, where he remained until August 2013, living as rotating machines technical executive, stayed in Actom Group. However, moving from LH Martinez to Marthinusen Coutts in September 2013, he has remained responsible for engineering and technical management. Rob, we are at your leisure.
Thank you, Jabu. Good afternoon, everybody. It's nice to see a lot of people listening in or watching in. We also joined this afternoon by Seth Nisi and Lucas Munyai from SABS. Seth basically runs this test laboratory and Lucas is his manager. So let's start off. Okay, once again, I'm not the expert in this. I'm almost just a messenger, but I feel it's a very worthwhile project to share, and for a number of reasons. And I think the best way to introduce it is it's a parastatal. And if you look at the state of parastatals in South Africa over the last 4 years, it's sad to say, but it's true that most of them have gone from an operational state to a largely unoperational state. And this is one exception to that. It's gone from a partly operational stage to a fully operational stage in the last sort of 7 months. So it's the SABS's National Electrical Test Facility High Power Testing Laboratory. There's also a high current testing laboratory, and I confused the two a while back. And the work was performed from November of 2019. We worked through the lockdown period under strict conditions. I think it's fair to say we had one COVID case who was not related, who was a technician working there, but he didn't get COVID at the time he was working there. So the work was performed by ourselves, Marthinusen Coutts. We're part of the Actom Group, and our sister company, Actom Turbo Machines. We did the electrical side, and Actom Turbo Machines did the mechanical. There were some other subcontractors, of course, notably the laser welding done on the rotors. So the presentation, pretty simply, what is NEFTA? Where does it come from? It has some interesting history. The history I'm going to give you is informal, so I welcome Seth or Lucas to correct me and add anything to the history, but it does have quite an interesting history. What does the plant do? It basically puts fault currents into devices that are tested, like transformers, switchgear, terminal boxes, etc. How does it do it? That's where the rotating machines interest factor comes in. It's done using rotating machines, and I'll explain more of that later in the presentation. There's with some interesting technical facts. Then specifically what work was done. You might wonder why that is 2/3 the way into the list of contents, and it's because until you understand what the plant is and what it does, it doesn't really make much sense to understand a scope of work on a plant like this. Then some challenges, they're inevitable. And why is NEFTA's high power lab so special and important? I'll leave that. It's unique in the world in terms of one aspect, and I'll mention that later, courtesy of my colleague Greg White at Actom Switchgear. A couple of acknowledgements and then questions or discussions. So the questions and discussions will come at the end of the presentation. Okay, the history. I think most of you listening in will know that ABB was formed out of Brown Boveri and SAIEE, a Swedish company, in the 80s. And at that time, when they merged, they found that they had two high power rotating machines based test plants. So one was offered to South Africa via a gentleman by the name of Andrew Eriksson, and involving Ben Janssen. Ben Janssen is the gentleman in front of the transformer on the right, together with a test engineer from Actom, which I don't know if Ben even knows I took the photo, so it's quite recent. So Ben was much younger at the time, and between them, the plant was offered to SABS, but they said no, they can't afford a plant like that, and the plant basically was offered as scrap and commissioned from that point. It was commissioned in 1996. It ran quite well. Then, due to maintenance issues, a couple of problems on the plant, and that it fell out of full action or full service for a few years. And as I mentioned in the beginning, we started work on it in late last year. We did the first current test on the 31st of August, and SABS kindly accepted the handover on the 1st of September. Okay, in order to introduce what the power plant is, it basically, as I mentioned, it supplies very high fault currents and high power fault currents into devices under test. This is a photo of the banner where you enter NEFTA, well, the high power lab. Remember, there's two other labs, and I'm only going to mention these three parameters here. The maximum voltage is 14,000 volts, the maximum test current is 40 kA, and the maximum short circuit three-phase power is 2,200 MVA. So it's a powerful plant. You can there will be material circulated about the plant. There's stuff later in the presentation about the more detailed capabilities, and you're welcome to ask Lucas or Seth at the end of the presentation any questions about the capabilities. A lot of you listening in or watching in will be aware of the capabilities. Okay, there's three drivetrains. They in front of us here. There's the two generators with their drive motors, and then there's the excitation train on the right. The generators are 85 MVA, 3000 RPM, 14 kV units. They are very special, and they are also very old, but they are classic proof that the older stuff works better in many cases. Okay, a little bit more detail. The plant doesn't end at floor level. There's a lot below the floor, the lube oil unit and other auxiliaries. There's a jacking oil system that jacks all the bearings of all 3 drivetrains to the point that you can turn it by hand. And it's crucial that that system operates and is maintained correctly. So the generators run up with these drive motors here. They each 1 megawatt, 6.6 kV. They're wound rotor induction motors, so they have big liquid resistor starters to allow them to run up. Now, a modern plant like this would probably use variable speed drives and squirrel cage induction motors, but these work very well, and they are very unusual in that they are 2-pole 3000 RPM wound rotor induction motors for the rotating machine specialists out there. Then the excitation drivetrain. So this drivetrain includes another drive motor, 800 kilowatts, also 6.6 kV. This drivetrain is 1000 RPM. It drives 2 DC generators with a 12-ton flywheel between them. And the 2 DC generators power the fields of the 2 generators. And the flywheel is there to overcome the armature reaction. My apologies. Okay, I'll show. I'm not going to go into the full detail of the plant, but basically, the 2 generators supply the fault currents. So you run the generators up, you get them to a certain voltage. The voltage is obviously calculated, and then based on what fault current is required, then the operator, or Lucas, Seth, will determine the reactor requirements that need to be put in circuit in order to produce certain fault currents. And you can see here that the generator connections, you either use 1 generator in delta connection, 2 in delta connection, 1 in star, or 2 in star configuration. There's your maximum voltages. With the 2, you never connect the 2 in series. They're always connected in parallel, because of course if you connected 1 in series, the stator voltage would need to be 28 kV, not 14 kV. And here are the fault currents that can be achieved from 10 to 40 with the different connections. What's interesting is when those of you who are synchronizing experts or know a lot about synchronizing generators to grids and parallel connections will ask, well, how are they synchronized? I found it quite interesting that they are just simply parallel connected before they excited. So that, and then you just excite them together, so they're permanently synchronized. You do need to make sure that the excitation is even or uniform between the 2. Okay, these are the main 2 generator drivetrains with one of our old greybeard specialist Butch Metzger in the photo. Now, why are the generators so special? Well, a typical alternating current generator, if it undergoes a short circuit, it's catastrophic. These things are designed to drive short circuits, and I'll show you a bit of the end winding detail just now. So as I mentioned, they are 85 MVA each. They operate rotate in opposite directions. The left hand one clockwise and the right hand one anti-clockwise. They don't run at exactly 3000 RPM because of course they're driven by wound rotor induction motors. So they have these units have a bit of slip, like 2990 RPM. So your test of your switchgear or whatever you bring to NEFTA will be done at sort of 49, something hertz, not at exactly 50 hertz, which I'm not a specialist, but I understand it's not a big issue to the test authorities. They were made by Brown Boveri Oerlikon many years ago, over 50 years ago. By the time the plant was moved to South Africa in the 80s, the plant was already about 20 years old. But they, as is obvious, they're still operating very well, and you'll see from the scope of work later. Okay, to illustrate the difference between how special these stators are, This, on the right, you can see a winding that we just recently completed of a 36 megawatt 2-pole. So you can see your Rubel bars, your transpose bars coming out here. You have top and bottom bars. They're connected in these blocks here and covered with these clip caps. And then the support you'll see around the end is a support ring that holds the winding in place. And then you can see roping here, 3 layers of roping. This is the NEFTA unit, and you can see it has the stator winding is almost completely encapsulated. So because you can imagine the short circuit forces, remember your end winding forces during a short circuit are proportional to the square of the current. So the overhang has basically got to be absolutely rigidly supported, and you can see that in the picture here, with very substantial vibration reducing components. Basically an extremely special design. What a designer might ask is by saying, well, if it's totally encapsulated and covered, what happens to cooling? And that introduces the next special aspect about these machines, is that they don't really need to cool that well from a continuous point of view, because they are only subjected to very short-term currents. A typical test is a second or two. So they don't have to have continuous cooling. That applies to the rotor as well as the rest of the stator where the coils are fitted in the slots. Now, how does the drivetrain work? Okay, for the generator fields, you need 800 volts at 1200 amps. That's the full rating of the field. So how does that come about? Well, it's basically with the DC. I showed you the DC exciters. Here we go. It's a 960 kilowatt, 1000 RPM machine, and it develops 800 volts at 1200 amps. And of course, there's 2 of them. They fitted to the same shaft. There's also 2 pilot exciters for lower currents, driven by 380 volt 3-phase AC motors. That's the nameplate of the AC motor. So, but the main function is really the main impulse exciters, or the main exciters, which are effectively just DC generators producing 800 volts at 1200 amps and supported by the 12-ton flywheel. A little bit of what it looks like exactly. Here's the drive motor, 800 kilowatt, 1000 RPM, 6.6 kV, also started via liquid resistor starter. Then this is the inboard DC exciter here, and then on the other end is another exciter for the other generator, and then here is the flywheel. It's covered by a guard for obvious reasons. And why do you need a flywheel? Well, the generators are flywheels in themselves because the rotors have got very high inertia. Now, what happens to the generators? The current that they produce is importantly linked to their speed, and if they loaded substantially and their speed drops, then the excitation, the armature output, in other words, the field current into the generators will be reduced, and this is all related to what is called armature reaction, where the currents, when the current is set up in the stator, it will oppose the current in the field as well. So if you basically have to have a very powerful supply to overcome the armature reaction from the stator fault current affecting the rotor. So that's the reason for the flywheel. Okay, then you've got the system. You generate this high voltage, and you need to produce basically different levels of fault currents for different times into different test objects. So this is a view from the one end. Most of the other views are taken from the far end here. Now this is from inside the switchgear compartment. Here you see the switchgear. So it's switchgear and reactors, a whole range of reactors in order to generate a the required fault current into the devices. And you can see air operated switchgear. I'll show you a little bit more detail about the switchgear. It's a little bit closer. You can see big arms. I'm not a switchgear specialist, but you can see all the reactors. Now imagine that these reactors are roughly 70 years old and still fully operational. So that gives you some idea of the reliability of this plant. Okay, the second part of the switchgear and controls, they're managed by Seth. He's an organizer here this afternoon, so you can ask him whatever you like. They're PLC. So although the equipment's old, that's PLC controlled, and the measurement interfaces are fiber optically isolated, so extremely safe. I love this red light in the corner of the room. That's what you want to see. The red light means the plant is operating, and basically much of your control is done here. This is your excitation control for generator 1 and generator 2. When you operate the two together, you have to make sure that the field current into them is approximately the same. What's important? Well, of course, safety. And that I mentioned the fiber optic measurement interfaces. There's massive thick concrete walls around the test object. There's a bunker between this test facility and the offices. Then your test time and test current. So your switchgear has to be very quick and accurately controlled. Then recordings are important. So here's a recording of the first fault current that we did on the 31st of August. It's quite interesting. I'll tell you about that later, what actually happened here. And in terms of the test, your most important aspect for a customer is actually a visual inspection after the fault, or a video recording. But the visual inspection that's what you check for. How did my equipment get damaged? Did it manage the fault, etc. Okay, now we can get on to the scope of work once you understand the plant. It's basically a full electromechanical solution. So where the responsibility for both the electrical work and the mechanical work rested with one contractor, which is very attractive to, in this case, SABS or any customer. So and there were a couple of subcontractors, most notably, as I mentioned before, our sister company Actom Turbo Machines. And so the scope was the removal, refurbishment and recommissioning of the two 85 MVA Oerlikon generators, their drive motors and all the exciters. There were commutators on the DC machines that had problems. The drive motors, amazingly, were still in very good condition. So then the liquid resistant starters were fully overhauled on site, the lubrication system, the ventilation system, the dewatering pump system. There was also a refurbishment of switchgear components, bus bars and bushings. And last but certainly not least, the cleaning and painting of the facility. And you can see by the photos just how impressive it turned out to be. It was completed by M&C and ATM, and the test facility was successfully commissioned on the 31st of August. Over here, this was the final 30 kA test that was done on the 1st of September. And then this 17.5 kA was very interesting. I was in the control room with Seth and a whole lot of other of us when this 17.5 kA was basically run into a partially open circuit. So you remember the slide I showed you of the switchgear. Imagine a Roman candle, sort of gigantic Roman candle coming out of that plant, and a lot of smoke afterwards. And Seth, in his typical calmness, goes in and has a look and whatever, and the next day they produced the 30 kA, absolutely no problem. In fact, I think that was later that afternoon. My apologies. Okay, a little bit more detail for the rotating machines people here. It was the refurbishment of the DC exciters and DC pilot exciters. So all old DC machines with commutators, old but very reliable. The refurbishment of all three drive motors. Now, those of you who know rotating machines, I think in my time I've seen 3 2-pole 50 hertz wound rotor induction motors. Remember that they have to have their rotor winding supported from centrifugal force. So they're very special machines. And it's amazing how well they operate, and how when you witness this plant running up the first time after recommissioning, you're in a sweat afterwards. Then you get to sort of 2 weeks later, and Seth ends up starting these drivetrains as if he's starting his car. So it's really reliable stuff. Then the refurbishment of both generator rotors, a little bit of more detail of that later. In situ cleaning of both generator stators, very important. A full re-wedge, so that's the stator slot wedges of the Gen 2 stator, and a partial re-wedge of Gen 1 stator. This was actually the most nerve-wracking part of the recommissioning, in terms of the generators still being capable of producing the 14 kV without problems, because the re-wedge is quite a sensitive process, especially for a 70-year-old machine that has never had any work done on the stators. The refurbishment of the liquid resistant starters by RWW, who were the manufacturers of them way back, and then the refurbishment of all drivetrain bearings. And this is where issues occurred. We found substantial cracks in the generator journals. That's the main generators, and not just the small auxiliary units. It's the main generators, basically the heart of this plant. Minor repairs to the lube oil system and minor repairs to the jacking oil system. This is the one rotor in our lathe in our Benoni facility. And this is where you'll see there's absolutely no ventilation. Normally you'd see ventilation holes, or you'd see ventilation features in a 2-pole cylindrical rotor like this, and you see nothing, because they're not necessary, because the unit is only under load, and one hell of a load at that, but only under load for a very short period. So what we found, which initially was a potentially catastrophic find, is quite substantial cracks in the main bearing journals of the generators. So under careful guidance of subcontractors, metallurgical specialists, welding specialists, etc., we machined into the journals, and they were laser welded and remachined to the correct dimension. And that was a substantial additional scope, which also added time to the project. Vibration. When we first recommissioned generator 2, it is experiencing something like 17 millimeters per second on the non-drive end axial in plane of the non-drive end bearing. And so what we did is we did some in situ trim balancing by Gavin De Beer. We managed to bring that vibration down by a factor of 3. And Seth and Lucas will comment later, but they were extremely happy with this vibration. They said they haven't seen that low level of vibration before. We also trim balanced Gen 1. All the other machines were balanced at full speed in our facility, and we also did slow speed balancing on Gen 1 and Gen 2 in our balancing machine in Johannesburg. Other additional scope of work, and I must mention this, Seth will comment about this as well. You know, there's always some awkward moments in these things where you want to hand over your part of the project, but then a protection relay starts giving hassles, and there was I think it's fair to say very good collaboration between all the parties. We had to one of these protection relays prevented us from starting a motor. We had to get a new one. We also, what we decided, this is the exciter drivetrain slip ring brush gear and slip ring assembly. It has never had a guard over it. So what we did is we made a guard as part of the project while we were busy. We also had those of you who have done commissioning or recommissioning, I always quote this, sometimes a little bit with trepidation, is that commissioning is 99% pure boredom and 1% sheer panic. I don't know who said it, but I've heard it a few times. So we had the boredom stuff like corroded or loose wiring. When we first started up the drivetrains, none of the 3 speed sensors operated. And they're like about 15 to 20 years old. Anyway, after 2 days, we managed to get all 3 working perfectly. Then because the 2 machines, the drive motor and the generator, are connected with a solid coupling, it's important to make sure that the axial magnetic center of the drive motor ties up with the magnetic center of the generator. And we developed a procedure to do that without actually fully exciting the machines, which ended up to be quite useful. So what was the 1% shear panic? And that's not what actually happened. That's part of NEFTA's presentation on a unit going under test. We had a slip ring compartment flash. We were standing about 2 meters away from the Gen 1 drive motor, and the brush tails basically short-circuited to the body of the thing. So that was shear panic number 1. And then I mentioned earlier, when this was when NEFTA connected the switchgear in and did a 16, or I think it's 17 kA. I think I've got that one out by 1. That loose connection occurred in the switchgear, and it was a sort of a reduced version of that, but it was a continuous arc for 1 second, because the test duration was 1 second. Then what we did is we added on the bottom right here, we added magnetic center markers to check that the magnetic centers were correct, and there's the speed sensors in position. This is where one of the culprits of loose wiring or corroded wiring came in, and it's amazing that can delay you for a day. And a day when you've got an entire team on a project is expensive. Okay, the importance of NEFTA to SABS' thing. I was lucky enough to be involved with NEFTA 3 times. When I was in 3rd or 4th year, I got taken there as a student when I was at WITS, and I was lucky enough to have Ben Janssen take our group through. And I remember we told us to stand behind a certain line when they tested a tiny little circuit breaker, and the explosion from that made all these macho 3rd or 4th year engineering students stand about 3 meters behind the next line when he brought a bigger piece of switchgear for the next test. So why is this lab so important? And I was reminded by a colleague of mine at Tom Switchgear. There's 3 of these test facilities globally. These rotating machines, high power test facilities. The one at NEFTA is the only one at altitude, and that is actually very important for testing. So that comes from Actom Switchgear, who have already used this test facility yesterday. That's how important it is to South African industry, that they used it within a week, just over a week of when it was handed over, and they're going to use it again next week. There's also a high voltage test lab, can do a lot of stuff. We will circulate a brochure of the NEFTA facility, of the 3 labs. I'm not going to go into too much detail. Then there's also a high current test lab, so specifically high current, not high power, can do 80 kA and also 10 kA temperature rise testing. This is the outside of the high voltage test lab. Those of you familiar with high voltage components will recognize this. Otherwise, it looks a little bit like one of Elon Musk's Mars setups. This is Seth here busy at the control room, in the control room. Okay, the NEFTA team. But the 2 people that are crucial here is Seth. Seth is the manager of the short circuit laboratory. So here's Seth here, and he's an organizer in this group. And Lucas Monyai is the senior manager of NEFTA, so of all the labs. And he's also in attendance here for your questions. There's a whole lot of contact details here for you. The presentation will be available, so you're welcome to contact them at any point. The Actom Turbo Machines group, Chris Besaidner, the MD and CEO. Roman Morna was the engineer responsible for the mechanical side. And you will see that most of the rotor work was mechanical and detailed mechanical work. And Kali Low managed the workshop side. So in this case, it was site services. There's details there as well, purely a mechanical and a specialist mechanical stuff. Then the M&C team, I'm going to do this very informally. Mike Chamberlain, he's our commercial and marketing executive. Craig Smurenberg managed most of this. He actually developed COVID during the commissioning thing, and I filled in for him, and I had some fun and games with the protection relay that Seth and Lucas will know about. Then this, I love this picture. This is Sibusiso Ndlovu. He's our Czech manager for power gen, and David McClung, a design engineer, who was also involved. They did a lot of the measurements. And this is inside the actual chamber that the test object is placed in. And I love the look of it, specifically when we're wearing masks. It looks quite very much like a torture chamber. And you can see your incoming bus bars and bushings here. I've said it that the concrete's about 1 meter thick. I didn't ask Seth or Lucas at the time, but that concrete is very thick. And there's a bunker built up between the test facility and the offices for further protection. And then our field services gentlemen, Ian Solomon, Andries de Lange, and Sergio. And here you can see the size of the generator with these gentlemen in the picture. Okay, this is detail on the NEFTA lab. I've included it here, so if you want to ask questions from Seth or Lucas, they can answer more detail here. But basically, this is if you want to do tests on distributional power transformers. Here's your kVA rating, your percentage impedance, and then further tables of what is possible and not possible on the plant. But you can also ask them questions about that. Okay, that's where I got the photo. This is what you can test at the lab: power and distribution transformers, dry type or oil immersed, medium voltage switchgear and control gear. As I said, Actom switchgear have already used the facility. And Greg White's comment to me was that the facility is extremely important for them. High voltage fuses, prefab substations, medium voltage flame-proof plug socket assemblies, substation conductors and accessories, high voltage switches, power cables, overhead line fault detection devices, current and voltage transformers, earthing and short circuiting cables. One that isn't here, my second involvement with NEFTA was when I was engineering manager at ABB's high voltage motor factory years ago. We tested a phase segregated terminal box with this plant. So that was my second involvement. And this is the third, obviously, so third time lucky. Okay, acknowledgements. As I said, I'm just a messenger here. I wouldn't have been as involved had Craig not contracted COVID. He's 100% at the moment, by the way. But I learned a lot from Seth, and I really enjoyed the interaction with Lucas, the two SABS gentlemen, team members. So anything specific about the plant and further testing, you can contact them. Actom Turbo Machines and their excellent team, to Marthinusen Coutts and their excellent team. As I said, very little credit goes to me. I'm glad we stuck with this project, because a lot of service providers will openly admit that they tend to lose faith in parastatal projects and lose interest because they won't think they're going anywhere. So that is why this is such an important success for us and SABS, and in my opinion for the industry in South Africa. And lastly, to the SAIEE, most importantly, to the rotating machine section for the opportunity to present this work. And the section will know that I offered to do this out of interest, and I hope that it's more than that, actually, that it leads to to this facility being used and used well. Okay, I've got two slides, one for discussion and one for questions, but what we will do is we will answer the questions via the panel. It'll be managed by my colleagues, and either myself, Seth, or Lucas will answer the questions. I suspect that it'll be mostly Seth and Lucas, but just a final thing I want to add is there is going to be an open day for the reopening of this lab. It will be sometime before the end of the year, and it will be opened by the Minister of Trade and Industries. You can watch the SAIE website with a notification. Otherwise, you can liaise directly with SABS. It's not open to everybody, unfortunately, but if you're close enough to Seth or Lucas or anybody else related, then I'm sure you can get an invitation. Thank you to everybody.
Thank you, Rob. That was certainly mouthful. You know, some of us, I must believe, I must say that, you know, we would not expect that we have such a facility in South Africa, and I'm very glad when I went through the SABS website and I look at what this facility has done in the past and already tested the 765 line with this facility. It's actually very amazing. And I must say, I think South Africa as a whole, as a country, I think we're up there with the best. And to have people like you, Seth and Lucas, looking after this facility, I think it was such a great presentation and also knowledge sharing with our colleagues. And we're also looking forward to much more of these things. And even maybe next time as a group, we'll probably have to ask Lucas and Seth to see if we can, you know, get a preview of this facility ourselves, some of us that have not been there. But certainly we thank you, Rob. And we're very fortunate to have been that time lucky to get involved in the facility of this type. So we thank you, Rob, for your presentation. And then now, colleagues, if you've got any questions, you are welcome to post them onto the webinar now on the side of the questions, and then we'll direct them either to Rob or Lucas or Seth to respond to the question. But one question, while we're looking forward to your questions, one thing I just want to find out from Rob and the team, I see you've got CRRs or coil returning rings. What material is that? Have you guys ever changed those ones? Is it still the 18.5 or still the 18.4, 18.5, or you've got the new material? Just the question on my part, please.
I speak under correction, but I don't. It's not 18.18. It's still 18.5. It's because they're still the original coil retaining rings. They were in very good condition.
Oh, is it? Oh, okay. Okay. The reason I'm saying this, okay, but it depends. The reason I'm saying this because at ESCOM we're replacing all the 18.5s, the 18.5 coil rings with the new spec because of them being susceptible to corrosion and cracking.
Yeah, no, I'm aware of that. But I think these machines are very special in terms of what I described, but they're also very special in that they are not continuous running machines.
Yes.
So
yes.
they often sit for quite a while without doing anything, or they're also in quite a safe environment.
Yeah, okay, because we don't have hydrogen and other cooling medium running through the generator. So obviously, I think they would be pretty safe in that regard. Okay, so any questions from colleagues? Joanne, can you see anybody? I can't see any. I see Richard Murphy. Richard Murphy, any question from your side?
Yes, Chair. I've got a question from Prof. Jan de Kok. These BBC Air Blast CB operates in 22 ms.
I think, yeah, he's pointing out the high speed, the speed of the breakers of the switchgear. that's used to control the fault current. As I say, I'm not a specialist in that. But that's his comment.
Yes, thank you, Seth. Good afternoon, colleagues. I should be able to answer that question. Basically, we do have these two master breakers, A+ breakers. Mr. De Kock, I think, is correct. Where these machines, these breakers can operate close enough to 22 milliseconds, but the actual opening time is about 28 milliseconds.
Thank you very much. And then I've got another question from Gideon Seil. When did the lab stop operating and what initiated the shutdown of the lab?
Hi, once more, colleagues. I will answer that one also. Basically, I think over the years, in terms of operation, the machines were non-operational for the past 4 years. But what caused these machines to be unoperational, it was due to foregoing certain maintenance requirements on these machines. So that's what led to them coming down. But even though they were down, one machine was still operational, but we couldn't really cover the whole scope.
Okay. Thank you, Seth, for that. Any other question? I only have that one as well, Joanne. Any other question from our listeners, from the colleagues out there?
Then I've got another question from Pelani.
Yes.
Looking at your machines, are too old? If there are, is there parts that is damaged? Is it difficult to get these spares?
I'll just partly answer that. The generators are extremely rare. I don't believe there's anyone who builds them anymore, who manufactures them, and if they did, you'd have to resuscitate a couple of greybeard brown Bavary specialists or Ulicon, most of them who have passed away. So they would cost an absolute fortune to manufacture.
Okay.
Thank you. Then
there's another one that Joanne talks about. How did you reduce the bearing vibration?
That's from
Mark Gideon, yes. Well, what we did is we did low speed balancing because they're very large rotors. If you to full speed balance them would have been done at Rotex facility, Eskom Rotex facility at great cost. But what we did is we balanced them at low speed and we trim balanced them. You saw the one picture where we had the 3 technicians sitting at the side of the machine, working on the side of the machine. You can run the machines up with the covers removed and balance the rotors in situ. So we had that specialist Gavin De Beer come along, and he puts his basically it's like advanced trim balancing on site. So he puts accelerometers and sensors on the system and a key phaser to reference the exact angle of the rotor at the time. And after a few test runs, he applies balancing weights in the same way you would balance the rotors in a balancing machine. And that's how we managed to get the vibration so low. So just the right skill with the right effort and meticulousness.
So just a follow-up question, Rob. So in this case, you did not do any hot balancing, it was just cold balancing, isn't it? There was no time when you excited the generator, for example, to see if it did respond to any thermal stability or instability. It was just cold balancing.
Yeah, I think to hot balance these, you'd have to get subjected to about 20 consecutive high current impulses. So I don't know. I don't think hot and cold balancing applies nearly as much to these units as it would to your Eskom units, Jabu.
Okay, thanks, Rob. Thank you. I see also, Joanne, there's another question from Lerato Mputle. Can you read that to us, Joanne? I can see faintly from my side. Hello, Joanne, are you there?
Sorry, Chair. I first have another question from Richard.
Okay, no problem.
Does this facility undertake main LVDB type testing, as we did have main LVDB testing in early 2000s? I have another question, which I will post after this, from Richard.
Yes, hi Richard. Yes, our facility is capable of testing distribution boards in our low voltage facility, which is our high current testing lab. Yes, we are capable.
Okay, Shab, yeah, let's take one or more questions, Joanne, also concerning the time as well.
Then we've got the question from Lerato. I've missed most of the presentation, but I heard Rob says that the rotor does not have ventilation holes. How are they normally cooled?
Okay. Because the hi Lerato, as I mentioned, the part that you missed of the presentation, which explains why you asked the question, is that these units run up at very low load. They just required to get to full speed, and they hardly endure any losses. So they don't warm up. Then they withstand an extremely high current that is very well, detrimental if they weren't designed correctly to them due to the forces, the electromagnetic forces, but the heating is very little, and most of the cooling will be adiabatic. So it will just be the conductors warming up and just dissipating into either the stator core or the rotor body. So they don't actually require continuous ventilation, hence the lack of ventilation features.
Okay, another question is, the type testing that was undertaken in early 2000 was done through NEFTA, auto transformer that was used. Were they able to get the 50 kA and 50 kA and 70 kA for 1 second after bus bar calibration was undertaken? That's the question. And also says these are on the website of my company. I'm not sure if that's a question or extra information. But do you know anything about that, Rob said, or?
That's said.
Yes, I will answer that. Yes. I think there's a follow-up question on that question. Yes, we did manage to do a 70 kA 1 second on a bus bar system. I think Richard is indicating that they did achieve that at our facility, but he's also asking whether we can do 11 kV testing. Yes, we can.
And 400 volts or something.
Yes, we can. Yes. That's
okay. Okay. Lucas, I hope your question has been answered.
Then I've got another question from Karabo. How many starts per hour allowed for these units?
Seth, I think that's yours. It's limited by the liquid starter.
Yes, that's correct. Generally, we have about 3 starts per hour allowed, but generally what we do, we restart them at high speeds. We don't usually drop down to 0 speed. So it's an auto restart every time after a shot, because when we do the test, we disconnect the machines from the grid and then we use the mechanical energy. So the PLC will just restart them at close to 2,500 RPM. So yeah, so in that case, we can do several starts at that speed, but only 3 restarts from 0 RPM.
Then I've got another question from Mark Gordon. Do they have student projects at NEFTA labs?
Yes, NEFTA do accept research opportunities for students and so on, but it will have to be approved through our executive. But we had some few students that did their research through NEFTA in the past.
Okay, Joanne. Just if in the absence of any other question, just from my part, Rob, you spoke about liquid resistors and your excitation, your commutator. Just help me understand these liquid resistors. What are they used for? And then the second one is the commutator. Does it have a diode? Are you still using diode? I see these are the old exciters. Do they use diodes, or what type of rectification do they use?
Okay, the liquid resistor starters, because they are wound rotor induction motors, they have slip rings where you connect an external resistor on for starting, and so that what you can effectively, typically a squirrel cage induction motor would have 600% starting current and maybe around about a 80% starting torque, one of that size. If you connect the right value resistor, you can get 100% starting torque with approximately 100% current. Now, when you're using a 1 megawatt 2-pole motor to run up an 85 MVA rotor, you want to be able to control that resistance, and that's what a liquid resistor starter is. Specifically, it's a set of fixed electrodes and moving electrodes in a sodium carbonate or soda ash solution to make a resistor that has a high power dissipation or energy absorption capability and a continuous variation of the resistance. So it starts high. The motors start up at about 80% of rated current, and they sort of hover around that as they run up to speed. So that's what the liquid resistor starter is. And very importantly, the limit that Seth's talking about on the starts per hour is determined by the liquid resistor starters, not so much the drive motor. Then commutators, the commutators are just mechanical like a mechanical switch to reverse the current on the armature of the DC machines. Okay. So it's your old commutator. It's not commutator in terms of power electronics or whatever. It's just purely these DC machines are brushed DC machines with commutators. And one of the commutators was basically had worn to the point that it could not be reused. Does that answer the question?
It does, Rob. Thank you very much. Thank you very much. I appreciate it. Okay, Joanne, any other question, Joanne, on your side? One more question, then. Yes.
One more question. It's from Andreas Butel. How accurate can the applied current and the time that current is applied be controlled?
Yes, this plant, we are capable of 1 electrical degree control on our making switches. So we've got very high speed making switch. So we are capable of making at any angle we want. So we can have test duration of up to 3 seconds, for example, 25 kA 3 seconds, 31.5 kA 1 second. So those are the typical durations that we have.
Okay. I think that is it sums up our webinar, colleagues and friends. I think we had a very interesting discussion today, and we wish we had the whole day to discuss something like this. And hopefully we will get Rob, Lucas, and Seth in the future to come and give us more. Because, like I said in the beginning, you know, we're living in South Africa, but sometimes, you know, we don't know if this thing they exist. You think they're somewhere else in America or you know, or Germany, but we have this thing right here in South Africa. So we're looking forward to more opportunities on this discussion. But other than that, for the questions that you still want to pose, you're more than welcome to continue posing them. And the panel, that is Rob, Seth, and Lucas, will answer them, and you get all your answers from the SAIEE website through the rotating machinery section. I think from my part, thank you very much, and stay safe. And yeah, I don't know from you, Jayan, I think that will be all from my side. Thank you very much.
I just want to give a big thank you to Rob Melaia, the presenter who presented this presentation. I also want to thank Lucas and Seth for answering questions, and thank you for everybody's time. This presentation will also be available on our SAIEE website. But thank you very much for all who attended, and be safe and take care. Anything from your side, Rob?
No, thank you to everybody. Thanks, Jayan. Thanks, Jabu. Thanks, Minx. And thanks to everybody who joined us. Thanks to SABS, Seth and Lucas. And I hope to see this plant running, that light burning often in future.
Thank you, Rob.
Thank you. Then the presentation has come to a close. Thank you, everybody, and take care and be safe. Goodbye.
Thank you. Okay, bye.
Thank you.